Good morning to everyone. So last year at this sponsors meeting, I presented about an waveform inversion methodology to simultaneously estimate for the microseismic source parameters such as location, origin time, and moment-tensor. And now this time in this presentation, I'd like to present more synthetic examples using this methodology and also show some preliminary results of application of this methodology to field data. So the objectives of this presentation are first to test this inversion on synthetic examples under different assumptions such as limited aperture first, and also sparse receivers, and also the presence of noise. And well, in this case, we try to apply this inversion to field data, and I'll show the results here. So to start, this is the wave equation that we use for modeling an inversion. That is the elastic wave equation for a heterogeneous and anisotropic medium. And on the right-hand side of this equation, the seismic moment tensor is represented by letter M. And in this case, we assume that seismic propagation and generation occurs in 2D, in the vertical plane defined by the coordinates x1 and x3. And that's the reason why the moment tensor has the shape that you see here, with three independent elements, M11, M13, and M33. So now consider this 2D fault geometry that we use in our inversion. In this case, the fault plane of the fault plane coincides with the vertical axis defined by x3 and x1, and theta is the deep angle of the fault. So in BTI media, the moment tensor components that we need are given by the expression shown here, where capital sigma is the fault area, D is the magnitude of the slip, and the C's that you see here are the stiffness coefficients of the medium. So we take these expressions and include them in a finite difference scheme, and then we are able to model any moment tensor source in 2D. So as it's usually done for microseismic data, in our problem we try to estimate for different parameters, a total of 6, 2 source coordinates, the origin time, and 3 moment tensor elements, M11, M33, and M13. As input data for our inversion, we use the in-plane polarized waves that in this case are the P and SV waves. And at the receiver locations, we record the horizontal and vertical displacements U1 and U3 that are also used for our inversion. The first equation here shows the objective function that we minimize in our problem, the L2 norm of the data difference between the observed and predicted data. And also, before in the last sponsors meeting, I showed the derivation of the adjoint state method for this problem that we use to calculate efficiently the gradient that is needed by waveform inversion. So here in the bottom equation, I show only the gradient with respect to one of the parameters, that is the source location. And this formulation using the adjoint has the advantage that potentially the anisotropic velocity analysis can be included into the inversion. And as it's the case for velocity analysis, here we need initial estimates for the source location, origin time, and we also need accurate initial estimates for the moment tensor, because as you can see in the bottom equation, the gradient with respect to the source location depends on the moment tensor, and this dependency creates this need for an accurate moment tensor. So now let's consider this homogeneous BTI medium with one microseismic event and a vertical receiver array and each vertical grid point contains a receiver. So the initial estimates for this inversion can come from other techniques such as kinematic inversion, for example, or even time reversal. So here I'm going to show how backpropagation of the adjoint wave field can help us constrain the source location and maybe also the moment tensor. So consider that we start with this homogeneous model shown before, and then if we backpropagate the adjoint wave field from the receiver locations, we backpropagate it until we get to the source location, that is where the perturbation in our model parameters is located. So from this focusing, we can give initial estimates for the source location, and by analyzing the focusing, we can also maybe give initial moment tensor estimates. So also last year I showed the results of inversion for this homogeneous model that you see here, and well, I showed that we are able, for this simple geometry, we are able to get to the right solution, almost exact. But now, what happens if instead of having full aperture, we have significantly reduced aperture, and we also have a sparse number of receivers? So, as we can expect some differences from the actual values. So this is the inversion. The behavior of the objective function with respect to iterations, and in this case inversion was performed under the assumption that the origin time is fixed and we only invert for source location and moment tensor. We are able to get to the right solution after around 15 iterations, and as a way of comparison I show the objective function for the case with full aperture, and okay, so this is full aperture, and in the red curve is converges more rapidly than the blue curve. Now this is the estimated horizontal coordinate, and as we can expect for reduced aperture, we have some differences with respect to the exact values indicated here by a dashed line, horizontal line, for the vertical coordinate x3. For the moment tensor element M11, M33, and finally M13. So in general, for all the parameters there are slight differences, but still we are able to get to an acceptable solution. So now let's go back to the homogeneous VTI model that we showed before, and this time we go back to the case where we have full aperture, but in this case, we assume that the observed data in our inversion is contaminated by noise, as you can see here for the vertical displacement of the recorded at the receiver locations. So the magnitude of the noise is 7% of the maximum amplitude in the observed data. And now let's see what happens when we perform inversion under these conditions. This is the objective function as a number of iterations for this example, and in this case we are not able to reduce the objective function as much as before because of the presence of noise, as it's expected, but still when we see the plots for the parameters, you'll see that we're able to converge. So as a way of comparison, again, I show here the objective function for the example with no noise, that of course converges much more to a smaller value. And then these are the estimated parameters. First, the horizontal coordinate that we are able to estimate with a high accuracy despite the presence of noise. For the moment tensor element M11. And finally, for the moment tensor element M13, the inversion is not as stable as for the other parameters, because this is the moment tensor element that is most sensitive to the quality of waveform matching. So far I've only showed synthetic examples, but now I'm going to introduce this preliminary results that we try inversion for this case study. So this data set comes from the backend field and was provided to us by Dr. Vladimir Grechka. And as initially it has some processing from the company that acquired the data, and the section and backend field is composed by five layers, 5 BTI horizontal layers. And the microseismic events were recorded at 2 different well locations, but here we only use one for inversion. And as input for inversion, we only use the direct P and SB waves. So the Thomson parameters for this backend field were estimated by Grechka and Jaskevich in 2014 by performing an isotropic velocity analysis using travel time inversion. And the layers that you see here highlighted in blue were originally found to be triclinic, that is the most general and isotropic system. But in this case, we assume, well, we take the best fit BTI model and perform inversion under the assumption that all layers are BTI. The geometry of the experiment is shown in this slide, and you see that the velocity model is very simple, and it's not able to produce the large coda that was recorded in the data. And for inversion, we only use one microseismic event indicated here by the red dot, and we choose one of the wells that has 14 receivers shown here in blue. This is the vertical component of the displacement that was recorded at the field. It contains P and SB waves mainly, and it also has a very long coda that we are not able to handle with the modeling code because of the limitations in the velocity model that I showed in the previous slide. So when dealing with this field data, we face different issues. The first of them is that the entire coda cannot be simulated because of the velocity model that I showed before. Then the second one is that we have no initial estimates for the wavelet because we are dealing with passive sources. Then we also don't have initial estimates for the Moment-tensor, that is something very important for our inversion. And then the final complication is that we are dealing also with very high frequencies in the range of 400 to 500 hertz, which means that our modeling requirements should increase, such as the grid spacing and time sampling. So we face also this problem. So how we dealt with these problems? Well, first, with the issue that the entire coda cannot be simulated, what we do is window the original data that was recorded in the field, shown in this slide again. So we window the direct P and SB waves, as you can see here. And we also shorten the length of the seismogram to make modeling less expensive and faster. So with about the issue with the unknown wavelet, what we do is extract this wavelet from the data. So we take the windowed data from the last step, and then we choose the P waves as the source for our extracted wavelet. Extraction is consistent if we choose to extract the wavelet from different receivers. So we choose the P wave because it's less affected by the attenuation effects. And then this is the extracted wavelet. And then the third issue is that we don't have initial estimates for the Moment-tensor. So what we do is in our modeling code, in our elastic modeling code, we use a dislocation type source, and we modify the value of we modify the magnitude of this dislocation type source, such as the synthetic data produced by this dislocation type source has a comparable amplitude to the amplitude present in the observed data. So the chosen model was this combination of the moment-tensor elements shown here, and also the data simulated with this dislocation type source. So now I'll show the results of inversion after all these considerations. This is the objective function as a function of the number of iterations. We are able to converge in few iterations. I show here only 15. And this is again the synthetic data, initial data that was calculated with our dislocation type source. And then after inversion, you see that the wavelet and the amplitude is essentially the same, but we get a small shift, and this shift, this time shift, allows the inverted data to be kinematic, to match kinematically the window's vertical observed displacement, as you see here. Now the plots for the inverted coordinates are shown here. We are able to get an update of less than 2 meters, which is a very small update. And then this is the update for a vertical coordinate that is also very small. And this update should be small given the high frequencies present in the data if we want to avoid cycle skipping problems. If we want to avoid cycle skipping problems, but if we want to avoid cycle skipping problems even more, then we should reduce the frequencies in our data and invert only for the low frequencies so that we can get a larger update. So to summarize this presentation, I presented some additional synthetic examples using the methodology that we presented before. And we also showed some application to field data, showing some preliminary results. The inversion is able to estimate source location, origin time, and moment-tensor simultaneously. And the synthetic tests shown here indicate that aperture can be limited and also receivers sparse. And the inversion is stable in the presence of a moderate amount of noise. And the preliminary data results show that, well, the moment tensor is not very well constrained, but we are able to estimate the source coordinates with some accuracy. So future work in this direction would include, first, multi-scale approach to use the low frequencies in the data that would help us get a larger update, and then to take full advantage of the adjoint formulation, perform an isotropic velocity analysis, and finally 3D inversion that would allow us to constrain inversion better for field data applications. Now, finally, I would like to acknowledge first Dr. Vladimir Grechka for providing the dataset to us and answering many questions regarding inversion and the dataset, and also Esteban for helping us with the implementation aspect mainly. And finally, thank you for your attention, and then I'll be happy to answer your questions. Thank you.